start on time, so it is great pleasure on my part to introduce Eva Uribe, who will be presenting our seminar today. And this is a part of early career seminars that we organize in terms of pipeline of our students going through to national laboratories and continuing with their careers. The topic of today's talk will be Protactinium production in leading thorium fuel cycle. And I will read part of Eva's exciting biography. So currently she's a senior system research analyst at Sandia National Laboratories. As a system analyst, she teams across disciplines to provide unbiased and objective information and frameworks for decision makers to understand the risk, benefits, and consequences of option within complex national security landscape. She's currently working on advanced nuclear fuel cycle safeguards, spent nuclear fuel reprocessing, nuclear deterrence, nuclear non-proliferation, and cyber system analysis. So basically all that NSSC3 will be working on. Prior coming to the labs in 2017, she was a Stanton Nuclear Security postdoctoral fellow at CSEC at Stanford. And she was investigating implications of advanced spent fuel reprocessing capabilities in thorium fuel cycle on nuclear non-proliferation and international safeguard regimes. She graduated from UC Berkeley with a PhD in chemistry in 2016. And I'm happy to say that she was one of first fellow of Nuclear Science and Security Consortium starting in 2011. She conducted her graduate research as an affiliate of the Heavy Element Nuclear and Radiochemistry group at LBL. And her dissertation focused on understanding the interaction between aqueous actinide and lanthanide species and organically modified high surface area mesoporous silica materials using solid phase nuclear magnetic resonance spectroscopy. She also was very much interested in nuclear security policy. So she also collaborated with Goldman School of Public Policy and graduated from Yale in 2011 with the Bachelor of Science in Chemistry and double majoring in Political Science. And she was Next Generation Safeguard Initiative intern at Non-Proliferation Division at Los Alamos National Laboratory in 2009 and 2008. So great career. And I think our students in particular will be happy to hear how did you go from UC Berkeley graduate student and PhD to national laboratories.
Great, thank you.
One more regarding logistics. If you go down to the bottom, you have reactions and you can raise your hand so that I can see you. And you can ask questions, Eva agreed during her presentation or at the end.
Great, thank you so much, Professor Vujic. I'm honored to be here, really happy to be back talking to the students here. NSSC was a really formative part of my time in grad school. As she mentioned, I was in the chemistry department while I was at Cal, but nuclear engineering was really my second home in many ways. And so I'm really happy to be back talking to all of you, and I hope you'll contact me after this presentation if you want to chat more. See, gotta figure out how to adjust my slides. There we go. So I'm going to get into the technical portion of my talk in a little bit, but before I do that, I thought I would just give some background about myself, my education and early career so far, and then talk just a little bit about what it's like to be a systems analyst at Sandia. Because it's, I've moved away from doing basic research in the lab, any kind of basic science in the lab. I don't consider myself an experimentalist anymore like I did as a graduate student. And what I'm doing now is very, very different, but also I think represents a really important part of the mix of what we need to tackle challenging national security problems. So I'll talk a little bit about that, and then I'll go into the technical part of my talk, and hopefully we'll have time at the end for plenty of questions. So a little bit of background about me. I grew up in Los Alamos. My parents worked at Los Alamos National Lab. I was a lab kid. Always knew and admired people that worked at the National Lab, so thought I might end up there one day, and indeed I have. I did my undergraduate on the East Coast at Yale, and cold winters. That's how I would sum up that experience. And that's very much what brought me back out to California, I would say. So then I was at UC Berkeley right after that for graduate school in the chemistry department. My mentor at the time was Heino Nietzsche, and then also for a brief portion of time, Stan Prusen, as well as Carl van Bibber. Michael Nacht, who I'm sure all of you know very well, was also a very important mentor for me in graduate school. So you all are very lucky to have this mix of faculty helping you out. And then I spent a year, just under a year, at Stanford in their Center for International Security and Cooperation, where I really decided to buckle down on this issue of safeguarding thorium fuel cycles. And that work is a portion of the work that I now have taken with me to Sandia and continued, but not the only thing that I'm doing there. So I am at Sandia, California. And a lot of people don't know that there is a Sandia, California site. We are the same national lab as Sandia Albuquerque. So actually they don't call us Sandia National Laboratory. They call us Sandia National Laboratories because we have multiple laboratories. The site here in California is much smaller. It's about 1,100 people, but we're kind of a close-knit group. And it's literally across the street from Lawrence Livermore for anybody who has been to that site. So there are lots of opportunities there as well as in New Mexico. I just wanted to briefly say, yes, I used to be a chemist. I used to be in the lab a lot. My dissertation research was on looking at absorption of uranyl species onto organically modified mesoporous silica. I'm not going to talk about any of these results in detail. Happy to engage if anybody has specific questions later, but I was looking at studying the surface interactions of the uranyl species using solid state nuclear magnetic resonance, and did some of that work at Lawrence Livermore as well. The reason I mention this at all, though, is because it got me thinking about uranium. And I was interested in actinide chemistry in general, which led to an interest in reprocessing of nuclear fuels, because of course you get a lot of fun actinide species there. But in particular for uranium, oh, I should mention quickly that the applications that we were looking into, that we were interested in applying these mesoporous silica phases to were things like spent fuel reprocessing, geologic repositories, doing lab scale separations, immobilization in like a vitrification scenario, or even like environmental remediation. So never got to full on testing any of those applications, but it was kind of towards basic science towards those kinds of applications. As I mentioned, I started thinking about uranium. So I was using a uranium-233 stock that they had up at LBL because the alpha activity was higher, and I was doing a lot of my batch sorption experiments doing alpha counting. And so I needed, some uranium that had a higher alpha activity, and U-233 met the ticket. But it was really annoying to work with because I had to purify it every month or every other month or so. And what I sort of started to put together is, okay, it's mostly U-233, but there's a little bit of this U-232 species in here, and U-232 is not very long lived, and so the daughters grow in really, really fast, and they muck up your sample. And if you're doing kind of a gross alpha count across, like the resolution on the detector I was using was not that good, right? So I was doing a gross alpha count across all this, and my experiments were getting screwed up by these by some of these daughters. And so I had to constantly purify my stock. And I thought, gosh, isn't uranium-232 the most annoying thing in the whole world? So some of what led me to my interest in the thorium fuel cycle, in which uranium-233 and uranium-232 are made synthetically, originated with this very, my work in graduate school that I was doing with uranium. So origin story there. I wanted to mention briefly too, this is stepping completely away from the chemistry laboratory. I got the opportunity to engage with the Goldman School of Public Policy. Of course, probably many of you have taken the joint course that's offered between the Goldman School and the Department of Nuclear Engineering on the nexus between nuclear technology and security. Beyond that, Michael Nacht invited me and my colleague at the time, Patricia Schuster, to do some policy analysis work with him. And we actually ended up writing a chapter that ended up in an edited volume. At the time, I remember thinking, what am I doing? This is crazy. This has nothing to do with my dissertation. It's not forwarding. I was spending a ton of time and effort on it. It wasn't directly forwarding my research, but I did it anyway because it was very interesting work. And I was telling Carl this earlier when we spoke, but that experience of doing that and doing that work is probably 80% of what has been very useful to me bringing into my current role at Sandia. That experience ended up being highly relevant for what I ended up doing for my job, even though at the time it was a small fraction of what I was doing for my main discipline in graduate school. So I just say that to, say, don't be afraid to go out there and pursue these kind of side interests, and you never know where they might lead. So Sandia Systems Analysis and Engineering, that's my group at Sandia. In my bio, you heard a little bit about it, but we're a group that hires master's and PhD across disciplines. Most of them are engineering and physical sciences, but there's also several social scientists that have come into our group over the years. And we team across disciplines in sort of like a think tank or a consulting type capacity. And so rather than answer the specific technical questions, we pull in SMEs from all the different areas, kind of integrate or bring together all of that knowledge and expertise and figure out, okay, is this what a key stakeholder or decision maker in the national labs or beyond, how do we bring all this information together to solve a problem that they are having? So this is just a quick slide to talk about some of the domains that we cover. Of course, our nuclear deterrence, WMD security, but then there's other things that are more out there, like cybersecurity, transportation and energy, disaster management. They did a lot of work on border security at one point. The point is really to help provide key decision makers with unbiased information to help them make decisions. So while it's definitely a step away from the laboratory, you pull in your technical knowledge and your ability to sort of break down problems systematically all the time. That comes in. I know we are soon going to be hiring. I think there's going to be positions posted. So if anybody is approaching graduation and interested, please reach out to me. It's a different life than doing basic science research, but one that I have found really enjoyable. I've loved it so far. And it's been about 3 years. So definitely reach out to me if interested, and I'll help try and connect you to the right people. All right, maybe I'll just pause here real quick and ask if there are any questions in the chat, or if anybody wanted to chime in on any of that.
I don't see any hands so far, so.
Okay, great. Okay, so I'll move on to the second portion of my talk now, which is all about a project that I started. It's now about a 1.5 years in at Sandia, but it really stems from a lot of the work I did as a postdoc at Stanford. It kind of had its origins there. And then when I got to Sandia and found the right team to work with, we expanded it. This work is funded by NA24, which is the Office of International Nuclear Safeguards. And I just wanted to make a quick plug. Federal program manager for that is Anaga Iyengar. Probably some of you know her. She is a Berkeley alum, I think, for undergrad. And she just was asked to start a new program within NA24 that this project is now part of, called ARISE, which stands for Advanced Reactor International Safeguards Engagement. And so Advanced Reactor Safeguards has really been elevated within their portfolio. And it's kind of an exciting time to be getting involved. I know we are right on the new proposal call for like the next year of funding just came out, and we are in the very active phase of brainstorming what kinds of projects to move on to and looking for collaborators at the university. So again, if this kind of thing sounds like it's right up your alley and you are interested in collaborating with us, definitely please contact me. So this is the team that I'm working with. I just wanted to give special thanks and shout out to Matt Gilbert. He's also a systems analyst at Sandia, also Cal alum. He comes from the physics department. And then several collaborators at Oak Ridge National Lab, specifically Louise Worrall, Nicholas Luciano, Natalie McCurl, Jeffrey Powers, and Richard Reed. We got a whole lot of guidance and advice from a lot of other people. But I just wanted to mention these folks in particular are the core team. A lot of the work that I'm presenting today was done by them. So to start off this talk, the question that kind of guided how we thought about this is, what if scientists discovered a new fissile isotope? And so there's some Spider-Man movies, Spider-Man 2, I guess, where you know, the bad guy discovers some new nuclear technology, and then in the end, Spider-Man is able to save the day. So if we're suddenly confronted with like this new fissile material, how would we go about developing international safeguards? I mean, the first question you might ask yourself is, well, how can it be made? You know, and what type of reactor or whatever, who is able to get their hands on this? How much could be made and how quickly? And what sort of constitutes a significant quantity? You know, there are some significant quantities that have been defined by the IAEA, but if this is a brand new material, how do we go about thinking about that? Is it feasible to kind of isolate it or divert it, or you know, is that not the case? And then if yes to sort of all the above, how would we go about monitoring and verifying it? And so we're not here dealing with a new fissile material, but we're dealing with something that we are calling a fissile precursor. And so protactinium within the thorium fuel cycle is this interim material that's formed on the way to the formation of uranium-233. So if you look kind of down in this bottom row, neutron absorption on thorium, and then it beta decays to protactinium-233. That has a half-life of 27 days, and then that decays to uranium-233. And there's a couple other examples that are in this table of what we would call fissile precursor materials. And so, you know, the focus here is protactinium. What do we do with protactinium, and why does it matter? So how do we learn to start worrying and sit down and study protactinium-233? Well, it persists long enough that isolating it from spent fuel, while not easy, is potentially feasible in some scenarios. And I'll talk about that more in a little while. And yet it also decays fast enough to accumulate U-233 on IAEA timescales. You know, so with a 27-day half-life, after about a year, it's over 10 half-lives, and so most of it has gone on ahead and decayed to uranium-233. Protactinium is vastly different. The chemistry is vastly different than, you know, anything else, I guess, on the periodic table. It's pretty easy to isolate it from thorium and uranium, for example. So it is feasible to chemically isolate it. And currently, it is not subject to material accountancy protocols or international safeguards by the IAEA. So even though it directly decays to U-233, which is accountable by the IAEA, protactinium itself is not. The precursor material is not. So we started to think through, you know, there's in the lower left of this frame, if we are looking at what percentage of some arbitrary isotope is remaining, you have this sweet spot that I've highlighted in green. If it's too hot, you know, it decays before anybody would have time to isolate a meaningful amount of it, right? If it's too cold, you might be able to isolate it, but it doesn't result in any kind of material of concern on a human time scale. But in this range of half-life, this is just right where you hit that sweet spot, and Protactinium-233 falls within that sweet spot. All right, so the key sort of policy question that this work is looking at is, should we think about, for certain fuel cycles, separately monitoring Protactinium-233 in order to meet safeguards material accountancy goals for uranium-233? Obviously, safeguarding uranium-233 is its own challenge. That is a huge ongoing research area right now. But in addition to those things that are being developed, are there cases where we would have to separately monitor just the protactinium or just protactinium isolation processes? That's kind of the key policy question. And I say it's a policy question because there's benefits and risks and consequences that have to be weighed here by the stakeholder in question, namely the IAEA, right? They know how many resources they have. They have to weigh, like, is the risk of somebody diverting something in a particular way worth us spending all of the resources and that would be required to develop some kind of new monitoring scheme? So that's why I call it kind of a policy question. There's not an easy mathematical yes or no answer here. So then the key research questions that we're answering with this project to try and inform that policy question is, okay, again, following the Spider-Man questions, how is protactinium produced? Can we identify what the leading candidate fuel cycles are? How much protactinium-233 is generated in each of these and sort of on what timescales? So for that, we teamed with Oak Ridge, who conducted some reactor simulations for us. Can protactinium be isolated on meaningful timescales? So that gets us into looking at the reprocessing and how do we think about how long it will take for us to get isolated samples of meaningful quantities. And then more what we're getting into this year and for our future work is, okay, once we've figured out which fuel cycles matter and which processes within these fuel cycles matter, how do we go about monitoring and verifying protactinium as part of uranium-233 safeguards for the IAEA? All right, so this part one, and I hope I'll go through these quickly enough to allow time for discussion. So part one, how is protactinium-233 produced? So protactinium-233 is generated in all thorium fuel cycles. I kind of said this before, neutron absorption on thorium-232, beta decays several times through protactinium-233 to form uranium-233. This is analogous so this process in the thorium-uranium fuel cycle is analogous to what we see in uranium-plutonium fuel cycles with the formation of plutonium-239. So in that case, plutonium-239 is the fissile material that gets bred in, and with thorium, it's U-233. This is just a slide to say it's not theoretical, people are working on it. There's a number of efforts. The biggest player is most likely India at this case. They have done a ton of research on thorium fuel cycles, but there are many others and myriad proposals out there for different ways to include thorium, even in existing like light water PWRs, for example, not even necessarily within advanced reactors. So Louise and her team at Oak Ridge had done some previous work looking at what are the most likely candidates for thorium fuel cycles to really be developed over time, and sort of what are the priority cases that we should look at. So we have piggybacked off of the work that they've done. And these are the ones that we decided, for better or worse, to focus on for this project. There are many others. There are many others that we could do in the future. So if you don't see your favorite on here, let's put it in the future work column and join us for our next proposal on how to expand this work. So what we've done so far is pressurized water reactors, looking at like a once through or multiple fuel recycling, where the focus would be to compare protactinium production rates for like a variety of fuel composition and then for fresh versus recycled fuel. So we ran a whole bunch of different starting fuel compositions for that case. Advanced heavy water reactors, looking at the Indian design, where we've been comparing protactinium production in different cores, startup, transition, and equilibrium cores. Again, from India, the fast breeder reactor, looking at protactinium concentrations in various places within the core. And then finally, molten salt reactors, we chose for a variety of reasons to focus on the MSBR as described by Oak Ridge, although there's many others that, that would be interesting to look at as well. So those are the fuel cycles we're looking at. So within each of these, how much protactinium-233 is generated and is it significant? There's a lot more data than what I'm going to have time to go through today. So I'm just going to highlight, give you the key highlights and then direct you to our forthcoming publications on this work. So first, how much protactinium-233 is too much? What is significant? Is 5 grams too much? Is 5 kilograms too much? You know, when we think about protactinium-233 decaying spontaneously to a significant quantity of uranium-233 within a few months, they start to become almost effectively one-to-one equivalents, right? It's just on a slightly delayed time scale. And the time scale matters. It matters a lot. But if we're thinking about, okay, here sits 8 kilograms of protactinium-233, in a year, it will be 8 kilograms of uranium-233, right? So a significant quantity of U-233 as defined by the IAEA is 8 kilograms. And so we're looking at, you know, a similar kind of thing for protactinium. And so this is a summary slide that summarizes a lot of our reactor simulation results. So this chart on the right-hand side just shows you over time, and you know, different reactors we're kind of using different scenarios for in terms of how long, you know, the operating lifetime and all of that. And so and then on the y-axis there is quantity of protactinium-233 per gigawatt thermal. And so you can see we were able to calculate how much protactinium-233 you've sort of got in the core overall per gigawatt thermal. That's just assuming like if you were to homogenize the entire thing, right? So for the MSBR, you get up to about 40 kilograms per gigawatt thermal. The AHWR, again, it depends on which core you're talking about, which initial starting composition. And if you're looking at sort of the initial transition or equilibrium core, PWR, it varies a lot by how much thorium you're kind of packing into your core. And that's the main driver there. And the FBR, you get about 20 kilograms per gigawatt thermal under the conditions that we modeled it. So that's kind of,
Eva?
Yeah.
For these reactors, what is the total mass of the core?
Oh, good question. I don't know that I have that off the top of my head.
Just like ballpark. I'm just trying to get a sense of like, okay, 30 kilograms, is that 2% of the total mass of the core, 20%?
So, okay, I don't have it normalized very well in my head on mass, but gigawatt thermal is, you know, I'm thinking about power output more. You know, I think there's a lot of reactors out there that are about a gigawatt or a half a gigawatt, right? So I would say that, you know, that is kind of a good metric for how much would be coming out of a single reactor if it was a gigawatt thermal output.
Yeah.
Does that help?
Yeah. Okay. Thank you.
Yeah, it's one thing we talked about a lot actually and went back and forth. Do we normalize to power or do we normalize to mass? On this page, it's kind of normalized to power output. Any other questions so far? Okay, don't be afraid to chime in. Okay, so, you know, the next question, can the protactinium-233 be isolated before it decays? If it sits in the spent fuel for a year or more, it'll turn into U-233. And then you don't have a protactinium problem, you have a uranium-233 problem, which is a problem, you know, to be looked at, but was sort of scoped out of what we're looking at, right? Because again, we're looking at, do you need to develop a separate monitoring process for protactinium isolation? So that's kind of what guided this. Well, as most of you know, there's different types of chemical reprocessing, and a really easy way to kind of frame this out is to say there's solid fuels like irradiated uranium oxide and thorium oxide, That would be in a PWR, a heavy water reactor, a fast breeder reactor. In some cases would be dealing with solid fuels. And in that case, you're most likely looking at, for commercial processing, you're most likely looking at a aqueous reprocessing scheme such as ThorEx. Briefly, you dissolve everything in nitric acid and then you selectively extract thorium and uranium into a separate phase, and then the fission products go in a different stream, right? The other option is if you have liquid fuels, for example, molten salt reactors. And so there we were looking at this multi-stage, what they call metal transfer process for the MSBR. And that involves, continuous online reprocessing to remove the fission products from the core. Processes like fluoride volatility will remove UF6, and then a process, I can't remember, am I going to go into detail? Maybe, maybe not. Liquid bismuth reductive extraction that would ultimately separate out your protactinium. And I do want to say that not all molten salt reactor designs call for separating out of protactinium. Some of them do, some of them don't. But we looked at a case, sort of, let's go with worst case scenario first, and then back off from there. So we looked at a case where MSBR, which does include protactinium reprocessing. And the other reason for that is that a lot of the current designs being proposed by kind of the front runners for thorium molten salt reactors do include protactinium processing. So that's like Flibe, and I think the TAMSR, from what I can tell, out of the Chinese Academy of Sciences. Somebody correct me if I'm wrong, but from what I can tell, also would include protactinium reprocessing. So, so these are kind of two different paradigms. Of course, with solid fuels, the standard operating procedure is the fuel sits in a spent fuel pool for 3-5 more years. And in that case, your protactinium would decay to uranium, and we don't have a let's safeguard protactinium problem. We have a let's safeguard uranium-233 problem. This question of liquid fuels is a different beast. So I am a chemist. So while I glossed over a lot of what was done on the reactor simulation side, I can't help but delve a little bit more into the chemistry side of things. So brief overview of ThorEx. So this is a process where basically you would dissolve everything in nitric acid. That's this aqueous phase here in blue. So you would get your thorium and uranium, your fission products, other actinides, protactinium kind of all dissolved together. Contact it with an organic phase that contains this compound tributyl phosphate, and tributyl phosphate selectively extracts uranium and thorium into this other phase. And really generally leaves the fission products as well as any protactinium that would be left it would leave all of that in the aqueous phase. So what's notable from this slide is that you're looking at here a case where you're separating protactinium from any of the native U-233 that would have been in your spent fuel, if you were to do it on a meaningful time scale. So that's one of the things we wanted to look into, right? Like, how long, or rather how short is too short to reprocess? And like I said on that kind of intro slide to this section, we know if you leave it a year, if you leave it the standard 3 to 5 years, you're not going to have very much protactinium left, right? But can we go in there and quantify at what point, within that first year, does it really cross over from this is a significant amount to this is insignificant? Because then we can go back and we can tell these key stakeholders and these key decision makers, if you wait 3 months, if you wait 6 months, if you wait 9 months, here is exactly what you're looking at quantitatively, and you can make your decision based on that, right? And then they'll design their kind of safeguards approach for such a facility accordingly, right? And so keeping in mind that ThorEx process that I described, we went through and did kind of flow sheet analysis on it and said, okay, in a simplified picture of this is that you're going to have 3 major areas where you might have protactinium streams coming out at the end. And that's in your aqueous waste. That's kind of your biggest place. Or you might have a little bit contaminating your thorium product or your uranium product. And these are kind of the 3 process streams coming out that you would want to know how much protactinium is in there. And so what I've done here in this table then is show for the different fuel cycles, PWR, advanced heavy water reactor, and the fast breeder reactor. If your reprocessing time is this time since shutdown, we've got 4 different cases, then how much U-233 from protactinium decay, that's the key, showed up in your aqueous waste after a year of reprocessing using like one of these, assuming a large scale, I think I assumed a 1,000 metric tons per year reprocessing capacity, right? So if you are full on, if your reprocessing facility is going at 100% for an entire year, using PWR, and we specify some of the composition here, and you're reprocessing within that first 90 days, and you're doing that for an entire year, you'll get like, you could end up with approximately 100, anywhere from 22 to like 120 kilograms of protactinium discarded to your aqueous waste every year. So that's separate from the U-233, right? I mean, the U-233 is here in uranium product. That's safeguardable by the IAEA, but everything that ends up in the aqueous waste, once it's uranium-233, it's also accountable material, but it ends up in a separate stream, right? And so you want to know where that's coming from. And until it becomes U-233, it's technically not an accountable material right now. So you're starting to get the idea. 90 days is super fast. Nobody does that. Nobody's planning on doing that. There's literally no commercial justification for doing that. So that's not a very likely scenario, but it shows you what we're dealing with. So after about 6 months, this really goes down to like the maximum you're going to get after a whole year of reprocessing is about 10 kilograms. Okay, that's still, a significant quantity of U-233, but it's pretty dilute, right? This is out of the entire output of a reprocessing facility. So you'd have to then concentrate that entire volume of stuff going through, right? By the time you get to a year, we're looking at more like 100 kilograms max, right? So what we can say definitively is between this 6 months to a year mark, the amount of protactinium in your aqueous waste, if you're reprocessing after about a year, 6 months to a year, is about as low as what it would be for normal uranium fuel. There's a little bit of protactinium-233 that ends up in that stuff too from, I think it's from alpha decay of neptunium-237. So right, it comes from the uranium-235. So once we're down to that low, we can say this is no worse than dealing with protactinium in normal uranium fuel, which we don't do, right? Already made the policy decision on that, right? So that's a guiding thing. And so then you can sort of do the same thing with the advanced heavy water and the PFBR. Okay, so switching gears over a little bit, let me just do a quick time check. Am I okay for time?
Yes, you're okay. There's 12 minutes.
Okay, I'll try and move through this quickly. So switching gears to molten salt reprocessing now, looking at this metal transfer process for removing protactinium. So the first step 1 is to remove as much uranium as you can. And that's because if you have too much uranium remaining in your fluid, it will screw up the second step. Let's just simplify it that way. Okay, so first they basically just bubble through fluorine gas and you get out UF6 gas and you can extract a bunch of the uranium that way. And so then you're left with salt that has a lot of your protactinium. Most of your protactinium is in here, and a little bit of your uranium is left in here. And it's a similar kind of thing. You contact that with a liquid thorium bismuth alloy, and it extracts. It reduces these to the metal species, and they extract to the molten metal phase. It does this process better, more efficiently with uranium than with protactinium. So that's where you have to get most of the uranium out. Otherwise, it will not extract very much of your protactinium. And then it leaves the fission products behind in the salt phase. So that's a little background on the chemistry there. And so again, we kind of looked at a simplified flow sheet for the MSBR and identified some of the key areas that you would want to know, okay, how much protactinium is ending up in these places. If you look at these flow sheets, like they've got everything flowing back in on itself. So there's very few places where you would have like a waste or a product coming out, right? And so that for this first cut, that was kind of the areas that we focused on. So there's how much protactinium is in the reactor, how much there is this step where they're looking at pulling out protactinium. That's for a variety of reasons, happy to talk about that. But pulling out protactinium, allowing it to decay outside of the core to U-233, and then once it does become U-233, feeding it back into the core. That really helps the neutron economy of the reactor to do that for the MSBR design. So there's this question of how much protactinium is in this decay tank at any given time, and then how much of that would end up getting discarded to salt waste. And just sort of a brief summary of the conclusions there. Within the reactor and reprocessing systems, it really reaches equilibrium after operating for about 3 to 6 months. And at equilibrium within the isolated salt, so kind of within the isolation system and within the protactinium decay system, there's about 100 kilograms of protactinium-233 at any given time. So 100 kilograms is, once that all decays to U-233, that's multiple significant quantities, right? And then also what we discovered is, based on kind of how they're describing operations, it appears that approximately 3 kilograms of protactinium will get discarded to the decay salt waste per year. So that then after a while would be approximately 3 kilograms of U-233 per year getting discarded to the salt waste. Okay, so some key takeaways from this analysis. Solid fuels, typically, as I said, solid fuel is not reprocessed until about 3 to 5 years of cooling. And really, after talking to a couple experts on this, the shortest feasible cooling time is 6 months. Like, there's no way anybody would do shorter than that. There's no commercial justification. So fuels reprocessed at 6 months or earlier, if anybody ever tried to do that, would may need some kind of additional monitoring and verification. But at this stage, it seems like an unlikely scenario to prepare for. So fuels reprocessed after 1 year have protactinium-233 levels similar to and actually lower than non-thorium-based fuels. Molten salt fuels are, as I said earlier, a different case. Online reprocessing there has a potential to remove protactinium from the core on a continuous basis. And so we're looking at like a typical 2250 megawatt thermal MSBR would have at any given time, like 100 kilograms of separated protactinium-233 at all times sitting on site. It is noteworthy that this protactinium-233 will generate U-233 of fairly high isotopic purity. And I think that's important also. And so it seems like a clear case to us that molten salt fuels merit a closer look at monitoring and verifying protactinium isolation in particular. So that is the focus of our work this year, is looking at the case of MSBR in particular, kind of a deeper level. I just wanted to give a shout out to the team. There's been lots of relevant publications coming out. Louise Worrell has been working on thorium fuel cycle safeguards for many years now. So I've put a couple of, just a sampling of those. I'm sure there are others. I wrote a paper as a postdoc. And also when I started at Sandia, I presented the paper at the IAEA Safeguard Symposium. We have a forthcoming report, like a Sandia report, that is going to be adapted into a journal article as well. So that's not out yet, but will be soon. And also an INMM paper that hopefully will be out later this summer. So finally, my sponsor, Annika, asked me to make sure to share with students in particular this non-proliferation energy.gov website because they have summarized here. So the URL is at the top. And this is a great landing page that gives lots of resources, lots of information about like potential summer courses or activities to get involved in. We all know that NA20 is really great about raising up the next generation, right? So I think NA24 is wanting to get a slice of the student population as well involved in this important work. So finally, I will take any questions or comments and just want to say again, please contact me. There's my email address for anything from specific questions on the technical content to what it's like to be a systems analyst or what it's like to be a working mom. Happy to talk about any of those topics. Thank you.
Great. You can use a reaction clap or something like that. So fantastic talk, both on your research that you're doing, which is extremely important, as well as your career and information that our PhD students that are graduating soon might use as well. I see some hands raised, and I also have a lot of questions. So let's go first to Raluca.
Thank you so much for the talk. I have a lot of questions, but I'll start with one. The separation scheme that is available to liquid fuel thorium-based reactors. Is that, are all of the possible options well understood there?
Do you mean this?
Yes, I mean that.
I wouldn't feel confident saying yes. So that's something we're looking into a lot more deeply. The first year of this work, last year, which is what I've showed here, was really at a high level. And, you know, the question of where protactinium ends up and how might, so what we've just started talking about recently, this is hot off the press, is, you know, if you have a scenario where you get striation of temperature in your molten salt, and what's going to happen with things plating out. You know, any relevant work that has been done was done by Oak Ridge like 50 years ago, and may or may not translate well to what's being planned now. So I would say there has been some work, but I don't know if it's completely understood. And that's
you mean in terms of the flow diagram or in terms of separations? I'm trying to sort of understand from your point of view, where are the parts that are most uncertain and most important to get more certainty around? Because obviously, you know, this field is evolving, and how the reactors are going to be operated, whether they're operated with an online reprocessing or with a centralized reprocessing, whether they have some kind of X-core cooling before the fuel gets brought back in, all of that is evolving. So I was really curious to hear more from your perspective. Where do you hope to get more certainty? Do you want to get more certainty on the flow diagram, or do you need to get more certainty on the different options for separations?
Yeah, well, there's a lot there. There's, you know, more certainty on design, like what are people really planning to do? And that's hard to get from the outside sometimes. You know, people don't share with everyone immediately what they're like planning for their brand new awesome design, right? So definitely it would be cool to get more certainty there. Like when I was briefly looking into for the TAMSR, right? Are they going to do protactinium separations, and how? You know, the best I could come up with is like a single PowerPoint that was given at Oak Ridge 3 years ago as part of some exchange where they mentioned protactinium separation, but not how. So I feel really like there's a lot of uncertainty there. But then I think there's also still uncertainty on like the fundamental protactinium chemistry side of things. And, you know, from my limited experience with protactinium chemistry as a graduate student, protactinium is like monstrously difficult to work with. And it's also hard to get anything other than trace quantities of it. And so, and it's like really, really hot. Very radioactive, right? Especially 233. And then 231, which is longer lived. So you could do the chemistry on 231, right? But it's longer lived, but it has like a really messy decay chain, and there's all these issues, right? So there aren't a whole lot of people doing like fundamental protactinium chemistry. And I feel like a lot of that stuff and how it will behave and in what people are proposing, like, is still not known. Shout out to Richard Wilson for people who know him. He's at Argonne, and he is definitely one of the few deeply looking into fundamental protactinium chemistry.
Okay, thank you. And Kathy?
Yeah, thanks so much, Eva. This has been really interesting. Also, it makes me wonder if all of the fluorinated salts is why Richard Wilson is doing protactinium fluorides instead of any other kind of protactinium chemistry, but that's beside the point. Maybe like a trivially practical question, but in terms of protactinium-233 monitoring, is that easy to do in terms of like, are swipes and counts like feasible in terms of the decay chain and separating it from U-233 or other parts like further up or down the decay chain?
Yeah, that's one of the things we're looking into this year. And so I think it does have some gamma lines, you know, with a lot of this stuff too. The concern is, of course, we could do destructive analysis. You know, we could take a swipe or take a sample and then, you know, digest it in acid and run it through a mass spec or something and get out what exactly do we have. But for a lot of these environments, like you're not going to have access where you can do destructive analysis. And so you're really looking at what kind of non-destructive instrumentation can we get in there, which sort of leaves you with what does the gamma spectrum look like? I can pull it up, but my memory is like protactinium-233 does have some, perhaps lower energy though. So any shielding might make that a challenge. Does that answer your question?
Yeah, absolutely.
Yeah, and then just a little tidbit on protactinium fluorides. Another reason that there's been a lot of focus on that is because at least within aqueous systems, and you know, obviously protactinium fluorides are highly relevant for once we start talking about molten salt, because those are fluoride salts in many cases. But at least within aqueous systems, like protactinium does not stay dissolved unless there's some HF keeping it dissolved. In almost every other medium, it starts to fall out of your solution. It just precipitates out and plates out. And so that's really frustrating. And so
I'm really aware of that fact.
Oh, okay. Yeah. So that's why the focus on, have you done some protactinium experiments?
We're trying to and struggling to get it into solution without adding HF, which
okay. Are you in Rebecca's group?
Yeah.
I didn't know you all are looking at protactinium. Okay, we'll have to talk. Cool.
Okay, great. I don't see any hands raised at this moment, so I will ask my questions. So just to let you know, there are two National Academy of Sciences studies or committees doing studies as mandated by Department of Energy. One is on the next generation of advanced reactors, and the other one is on front end, back end of the fuel cycle for advanced reactors, basically to figure out which reactor designs and fuel cycle are one, non-proliferating, two, produce the smallest amount of waste, both in terms of the amount as well as what is the composition. And then the question is for backend, do we do reprocessing or not? So for these several designs, I think 4 that you and your group analyzed, can you tell us a little bit regarding backend and reprocessing, or was through which one you might see in better light?
Let me go back to the list. I can figure out how to navigate over there. And let me see if I can summarize your question firstly. So from this list of
just in addition to specifying the amount of certain nuclides per gigawatt thermal, it is also good to specify based on mass. So just have both.
Okay. Okay. So is your question
as well as the composition and so on? So regarding these 4 designs that you have, which you think is less proliferating, for example, or if you are to reprocess, or if you are to have once through, basically you just put it underground. So which one might be of concern, or which might produce the better result?
Yeah, so this is a tough question. This is also a policy question.
Tough question. So I'm not saying you have to answer everything, just, you know.
Yeah, I mean, my personal thought, and I don't, I want to stay a little bit agnostic on, you know, do I think certain types of reactors are inherently more proliferation resistant, or all of that? You know, certainly there's there's extra steps involved, right? And that's always a good thing to make it harder. Once through, it helps. You know, if you are not separating stuff from fission products, that helps. I think the MSBR is, you know, this really interesting case that we have not been faced with before, because you're speeding up effectively reprocessing. You're doing super short cooled reprocessing, like zero cooled reprocessing. It opens up concern about these fissile precursor materials that didn't exist before, right? And so as we are advancing more and more towards technology that allows for really short cooled reprocessing or zero cooled reprocessing, this is a gap that I believe, in personal opinion, exists within the international safeguards and maybe probably domestic safeguards too, like framework for how to deal with those types of materials. You know, you go and look up in the terminology and like the safeguards glossary, and they've defined what's a direct use nuclear material, what's an indirect use nuclear material, what timescales and for what quantities of those do we need to be designing our safeguards approaches around. And these precursors fall through that gap. They don't fit neatly into any definition of any type of nuclear material. So I think liquid fuel poses a unique challenge. As to which like designs are more proliferation resistant, yeah, I guess I would summarize there and say I would prefer to remain agnostic on that question, but say for all of them, you're going to have to deal with safeguarding it anyway, even if it seems like it's notoriously difficult to divert material from. Like there's no feasible diversion scenarios. Nobody would do this. You know, we have set up our system such that the IAEA has to safeguard them anyway. And so it would behoove us to look at it, right?
Okay.
Did I answer your question, kind of?
Excellent. Anybody, quick question? I don't see any hands raised. So I would like to thank you very much for this excellent presentation on very important topic for, you know, back end of the fuel cycle, because if we are to go ahead and have advanced reactors in the near future, this needs to be addressed from many, many points of view. So thank you very much.
Thank you. Thank you for having me.
Thank you very much.
Thanks, Eva.
Thanks, everyone.
Thank you.
Thank you.
Please email me.